Welcome to a technical overview of Common Rail System. Common Rail Diesel Fuel Systems. Aims, Objectives and Disclaimer. The aim of this presentation is to give a generic technical overview of the main features and operating principles of the Common Rail Diesel Fuel Injection System. The objectives are that by the end of this presentation, you will have gained a working knowledge and understanding of the fundamental principles of Common Rail Diesel Fuel Systems. Please bear in mind that all facts and figures quoted are intended to show typical examples only for explanation purposes. Always refer to manufacturer technical data for exact system specifications and repair procedures. Advantages of Common Rail. Fuel pressure available on demand. Higher injection pressures and finer atomization of fuel. Injection pressure created independent of engine speed. Multiple injections per cylinder combustion are possible. Benefits of Common Rail. Reduction of overall exhaust emissions. Reduction of particulate emissions. Reduction of noise emissions. Improved fuel efficiency. Higher performance. Examples of typical Common Rail System maximum fuel pressures. Bosch. Generation 1. Up to 1,350 bar, 19,845 psi, Unijet. Generation 2, up to 1,600 bar, 23,520 psi, EDC 16. Generation 3, up to 2,000 bar plus, 29,400 psi. Denso. First generation, up to 1,450 bar, 21,315 psi, ECDU2P. Second generation, 1,800 bar plus, 26,460 psi, HP3/HP4. Delphi. Multec, up to 2,000 bar. Direct acting diesel Common Rail System, up to 2,000 bar. Various systems differ in design, components layout, and specific functions. However, all operate in a similar way. The fuel system can be divided into three basic circuits. Low pressure supply. High pressure delivery circuit. Fuel leak back and return. Components overview. Example show, Bosch EDC 16. High-pressure fuel pump. The high-pressure pump is the interface between the low-pressure and the high-pressure side of the fuel system. Basic function. To ensure that enough fuel is delivered at sufficient pressure across the engine's entire operating range. This includes delivery of sufficient fuel for a rapid engine start and pressure increase in the rail. Here is an example of a high-pressure fuel pump, Bosch CP3. This pump have several pumping chambers. Here is a cutaway view of the Bosch CP3 high-pressure pump. Pause the video to get a longer view, if you want to. The high-pressure fuel pump, fuel metering valve and transfer pump. Transfer pump supplies fuel from the fuel tank to the pumping chambers of the high-pressure pump. Fuel metering valve regulates the fuel intake volume to the pumping chambers of the high-pressure pump. Three pumping pistons are operated by a polygon ring on an eccentric cam on the pump shaft. As the pump rotates, the polygon ring moves in a circular motion to operate the pump pistons. The transfer pump. An electric pre-supply pump and fuel tank may be used instead of a transfer pump. Some systems may use a combination of electric pump and transfer pump. Fuel metering control valve. Located at back of high-pressure pump. Controls the fuel intake volume to the pump. Receives battery voltage supply from engine ECM. Energized by ECM via negatively triggered PWM. Operating frequency, approximately 180 Hz. Fuel metering control valve operation. When solenoid is de-energized, valve is open which cause low fuel volume intake to pump. When solenoid is energized, valve is closed which cause high fuel volume intake to pump. The fuel volume intake is controlled as follows. Valve is de-energized so it open causing more fuel to returns back to the tank in effect cause low fuel volume to pump. When the valve is energized/closed, which cause less fuel returning to tank, in effect causing a high fuel volume to pump. Advantages of fuel intake volume regulation. Only the required volume of fuel is supplied to the common rail from the high-pressure pump. Reduced fuel flow around system results in lower fuel return flow temperature. Reduced parasitic load on engine from high-pressure pump contributes towards further reductions in exhaust emissions. Fuel metering control valve failure symptoms and diagnosis. Solenoid circuit monitored by engine ECM. If an open or short circuit is detected, engine stops or will not start. DDC stored in mill illuminated. Mechanical failure of the metering control valve does not necessarily prevent the engine from starting. Mechanical faults can cause DDCs relating to positive or negative rail pressure deviations. High pressure regulator valve. System variant. Fitted to back of HP pump. Controls high pressure fuel delivery to common rail. Excess fuel returns to tank. High pressure accumulator, common rail. Fuel is supplied to the common rail at high pressure from the high pressure pump. The rail stores the fuel and distributes it to the individual injectors. It also damps pressure vibrations caused by the high pressure pump and injection processes. Typical volume of fuel held in common rail, 16 to 20 cubic centimeters. Typical fuel rail pressure with engine idling and at running temperature, approximately between 300 to 400 bar, 4410 to 5880 psi. Typical maximum possible fuel rail pressure. Approximately between 1600, 2000 bar, 23,520 to 28,400 psi. Health and safety. Due to the extremely high working fuel pressures in the common rail fuel system, never slacken fuel or injector pipes or try to disconnect components of the fuel system whilst the engine is running and high pressure is present in the system. Fuel rail pressure sensor. A fuel rail pressure sensor is located on the fuel rail. The fuel rail pressure sensor monitors the fuel pressure in the common rail. Typically a piezo-resistive type sensor. 3 wires, which are 5-volt supply from engine ECM. Sensor ground via engine ECM. Linear signal voltage output to ECM. Signal utilization. To enable the engine ECM to determine the fuel rail pressure. Used by the ECM as part of the calculation for the percent duty cycle applied to the rail pressure control solenoid and fuel metering solenoid. The engine ECM applies a stabilized 5 volts supply to the signal wire of the fuel pressure sensor. The resistive value of the sensor creates a change in the voltage on the signal wire relative to the fuel rail pressure. Typical signal voltages from rail pressure sensor, engine stationary, approximately 0.5 volts. Engine idling, approximately 1.32 volts. Snap acceleration, approximately 3.77 volts plus. Rail pressure limiter valve. A mechanical pressure limiter valve is fitted to some systems. It is located at the end of the fuel rail. Its function is to relieve rail pressure if abnormally high system pressure is generated. If excessive fuel pressure is generated, the valve opens a fuel return port. Excess fuel is relieved back to the fuel tank. Example operating pressure of rail pressure limiter valve, Denso HP3 system. Valve opens at 230 MPa, 2300 bar, valve closes at 50 MPa, 500 bar. Fuel rail pressure control valve solenoid. A rail pressure control valve solenoid is fitted to the common rail on some systems. The valve controls fuel pressure by opening and closing a return port in the rail. Excess fuel returns to the fuel tank via the fuel return. Receives battery voltage supply from engine ECM. Energized by engine ECM via a negatively triggered PWM. Operating frequency, approximately 1000 Hz. Used in conjunction with fuel metering solenoid, the rail pressure solenoid provides more accurate and faster control of pressure, particularly when reducing rail pressure during overrun. Rail pressure control valve de-energized. More fuel is returned to fuel tank via return port. Therefore rail pressure decreases. Rail pressure control valve energized. Less fuel is returned to fuel tank via return port. Rail pressure increases. Rail pressure control valve failure symptoms and diagnosis. Most likely consequence. Engine stops or will not start. Solenoid circuit monitored by engine ECM. Open or short circuit detected. DDC stored in mill illuminated. Engine stops or will not start. Mechanical failure. A minimum amount of fuel rail pressure is required to enable the engine to start. Typical value. Approximately between 200 to 300 bar. Rail pressure control valve failure symptoms and diagnosis. Continue. Most likely consequence. Engine stops or will not start. Solenoid circuit monitored by engine ECM. Open or short circuit detected. DDC stored in mill illuminated. Engine stops or will not start. Mechanical failure. Valve stuck open equals low rail pressure. Engine stops or will not start. Equals valve stuck closed high rail pressure. Engine stops or will not start. Testing rail pressure control valve. Multimeter. Test internal resistance of valve solenoid winding. Typical value, approximately 3.6 ohms. Diagnostic skin tool. DDCs and monitoring of rail pressure values. Oscilloscope. Test supply voltage and earth switching signal from engine ECM. Test stability of waveform. Pressure control valve waveform, engine idling. Pressure control valve waveform, snap acceleration. Pressure control valve waveform. Remember, the engine stops or will not start if the fuel rail pressure and control valve fails. Fuel injectors. The fuel injectors are controlled by either a solenoid or piezo actuator. They are energized sequentially by the engine ECM. The ECM simultaneously switches a live voltage supply and an earth for each injector. Multiple injection processes per cylinder combustion are possible. Fuel injector's parts label. Solenoid actuator. Nozzle spring. Injector valve. Valve piston. Thrust piece. Valve needle. Fuel leak back, return. Electrical connection. High pressure fuel inlet, from common rail. Operation of fuel injectors. Fuel pressure is supplied to the injector needle seat area, and also to a small chamber above the injector piston via a calibrated inlet port. When the solenoid is energized, the injector valve opens. Fuel pressure is relieved above the injector piston and returns to the fuel tank via the injector leak back, return, ports. This creates a pressure difference above and below the injector piston. Fuel pressure below the injector needle lifts the needle. Fuel is now injected into the cylinder. Maximum stroke of solenoid valve. Approximately 50 micrometers, 0.05 millimeters. Piezo injector. Primary advantage. Quicker response time, up to 4 times faster than solenoid-controlled injector. Features. Piezo stack has several hundred wafer-thin slices of piezo crystal material. When voltage is applied, the piezo stack expands and opens the injector valve. Mechanical principle of operation is similar to the solenoid injector. Injector codes. Most injectors have a code that must be programmed into the engine ECM. The code relates to the calibrated flow rate of the injector. It enables the ECM to correct the injection quantity to compensate for manufacturing tolerances. Oscilloscope waveform, solenoid injector de-energized. Oscilloscope waveform, solenoid injector energized. Oscilloscope waveform, piezo injector de-energized. Oscilloscope waveform, piezo injector energized. Engine management closed-loop control functions. Rail pressure calculation. Example. Bosch EDC16. 2-point control. Engine management closed-loop control functions. Rail pressure calculation. Example. Bosch EDC16, 2-point control. Fuel system diagnosis. Common rail diesel fuel systems operate on a closed-loop basis. The system carries out a great many complex calculations to precisely control fuel quantity and injection timing. A range of tools and test equipment is commercially available to assist with diagnosis of the system. The following is a brief overview to highlight some of the basic tests that can be carried out to diagnose faults with the system. Fuel system diagnosis. Basics first. Sufficient diesel in the fuel tank. Fuel contamination, e.g. from petrol. Fuel leaks and damage to components. Battery state of charge. Adequate low-pressure fuel supply from fuel tank. Does engine start or crank and try to start? Is white smoke emitted from exhaust during engine cranking? Not always easy to see but indicates some fuel is entering cylinders. Are any DDCs stored in fault memory of engine ECM? Fuel system diagnosis. Is the system capable of generating sufficient fuel pressure? Typical minimum, manufacturer specified, value during engine cranking. approximately between 200 to 300 bar. In practice, the figure is usually higher for a good system. Above example shows fuel pressure during engine cranking. Fuel system diagnosis. Injector leak back test. There should not normally be any fuel collected in receptacles during engine cranking. Example of acceptable leak back value with engine idling. Approximately 20 ml per injector over a 2-minute period. Always refer to manufacturer data for exact specifications. Fuel system diagnosis. Maximum fuel pressure. Thank you for attending a technical overview of common rail diesel fuel systems.